Alright, so today we're going to talk about my final project here, which is 3 different methods of approximating a single variable integral in Python. The first method is the trapezoidal method, and it takes a curve and it'll break it up into a bunch of small trapezoids. When you take the area of each of these trapezoids and you sum them all together, it'll give you an approximation of the area under the entire curve that you're trying to integrate. So as n increases, the number of trapezoids increases, they get smaller and they become a better and better approximation of the function that you're trying to find the integral of. Alright, so just do an example over here. We have imported math and integrate, defined our function to be, in this case, 3x squared plus 10, just because it is an easy function to check the answer for, so that we can see that it's working correctly. So all 3 of these methods will take the same 4 arguments. It'll take the function f of x. It'll need a lower limit of integration. It can be positive or negative. An upper limit of integration, and then the number of divisions that you're going to break it into. In this case, our number is the number of trapezoids. And again, as that number increases, so if we just do a 10, then it'll be not quite as accurate as if we run the function again, but we use 1,000 trapezoids. This will be a more and more accurate approximation as you use more and more trapezoids. So the next one is Simpson's 1/3 rule. It works in a similar way, and it takes the same arguments, but instead of breaking the function into small trapezoids, it breaks the function up by its curves into paraboloid sections. So if you run this one again the same way over the same bounds of integration, then you'll get a very close approximation of the correct answer. So the only problem with Simpson's rule is that you cannot integrate, or you cannot have n to be an odd number, right? N must be even when you use Simpson's. So if you try to do it, because you can still get an answer, it just won't be accurate if you use an odd number. So we have to put a break in there to prevent that. Alright, so the last method is Richardson's extrapolation on the trapezoidal rule. So the way that this one works is it runs the trapezoidal rule, and then it runs it again, but with twice as many ends. So if you run this on the same function, it'll give you a smaller margin of error, which doesn't necessarily mean that the answer will be better, but the majority of the time it will be. Okay, not on this one, I guess, but it'll still be accurate the more the more times that you break it up. Right, so there we go. This one, it uses the trapezoidal rule and then the trapezoidal rule again with twice as many ends, and it weights them. It assumes that the time that you use more ends, you will be more accurate, but it still takes into account the the lower number of n's. So the more accurate you are, the smaller your margin of error is. When you use a very small number of n's, then your range is too wide and it subtracts out too much. That's why the first answer was so far off. So these three functions can be used on any single variable integral, but most of the time you could find an exact answer, but that's not always the case. So I would suggest that they be used most often when you have a function that cannot be easily integrated, or cannot be integrated at all, maybe. So the function e to x squared, this function does not have an antiderivative. E to x squared, yes. So this function, the best that you can do at any time is to approximate it, right? So this function gets very large very quickly, so we'll use some smaller numbers, but yeah, this function, you cannot find an antiderivative for it, so you have to approximate the value. Oh, oops, I didn't, that e doesn't exist, so we return math.e to the x squared, and it'll probably work better because e by itself doesn't actually mean anything. Alright, so let's try again. From -1 to 6 on e to the x squared. There we go. So yes, very large number, and you can't get the exact answer, so that's the closest you're going to be able to do. Alright, well, not the closest. You could add more n's and then it'll be closer. But that's about it. Thanks.